in this topic we are going to talk about PID tuning. So, we are basically going to look through Ziegler-Nichols method and Cohen-Coon method, and we have just given an idea of all these things, and you can try out with all these formulas. There are a lot of formulas for PID tuning, like there is a lot of ways in which you can tune the PID controller. So, these are some of the most commonly used methods. So you can also try using these things, and you can refer the literature, like there are a lot of tools for PID controllers, how to tune the PID controllers. So you can use any of the methods and see like what each method claims, etc. So basically you will get an idea of what these two methods are. So again we take the system to be some process which is going to have a transfer function 1 by s cube plus s square plus 2s plus dot 0.1. So again remember when we say this is the transfer function, this is the transfer function of the system or the process. So we are the process, so we get a linear model of it around the operating point. So why I am telling this is because, like so let us say I have to maintain the temperature of the boiler to be like at 200 degrees Celsius. I am just telling some numbers, random numbers. So this if you take a boiler to be a nonlinear equation, like if you take it to be a system which is nonlinear, then basically this transfer function will vary when you if you linearize the boiler around say 200 degrees Celsius or 150 degrees Celsius or 50 degrees Celsius. So it is important, like this transfer function is like around which point you get this transfer function. So what we normally do is we linearize the system around the point at which we tend to operate, so at which we decide to operate. So that's what we say, that's the operating point. So I want to maintain the temperature of the boiler at 200 degrees Celsius. So what I will do, I will tune the PID controller like around the operating point. So I will linearize the model around the operating point, and then I will get a model of it, and then I will try to use that model to find the PID gains. So there are different methodologies when you have a very nonlinear model, but this is the idea you have to have. Like basically you linearize system around the point at which we decide to operate it. So if you use a basic PID controller structure. So and this is the system which we have already seen, and we found like okay we found the ultimate gain value to be 1.9. Ultimate gain value is the gain at which system will start going into the oscillations. Basically it is the gain at which the poles of the closed loop poles are on the imaginary axis, if you can remember the root locus, and it's also the gain margin of the system. So everything is related, right? So that's what we saw in the previous thing, and the critical frequency is approximately 1.4. So this is what we have seen before. So now from you can use Rauter criteria. We already solved it, but again we can solve it, like you can put s cube, s square, s1 and s0, and then you can put like 1 2 here, and then 1 and 0.1 here, and basically we have to remember we have to use Rauter criteria for a closed loop transfer function. So basically when we have a transfer function like this is a set point, and this is the summer block, and this is the gain transfer function, and then you feed it back. Basically what you have is closed loop transfer function is nothing but k by this is g of s. So basically s cube plus s square plus 2s plus 0.1 plus k. That's what we already saw in the previous lecture, this one, but still again we are writing it down so that this becomes 1 by kp. And we also saw that when this will become 0, it's becoming like you have like 2 minus 0.1 plus k by 1. So that is when this will become equal to 0, and this we say like if this is positive, this doesn't care. So basically we can take like k equal to from this, if you equate this to 0, we get k equal to 1.9. So this is the ultimate gain value from Rauter criteria. So we already saw this in detail in the previous lecture, so you can go back and see, but this is the simple thing to find what is the ultimate gain value. So again also like taking the root locus or taking the body plot, whatever technique you use, it has to come the same thing, right. So basically if the same system, if you draw the root locus is drawn using the open loop transfer function, okay. So as we vary the gain, it crosses the imaginary axis at a certain point, and if you see what is the gain at the imaginary axis at this point, then it basically it's like 1.93. It's not exactly the imaginary axis, it's somewhat tilted little towards the right of the plane, but you can imagine like it's less than the gain, it's increasing the gain, right. So to on the imaginary axis somewhat close to 1.92 or something, because that's what this pole is not on the imaginary axis, so this is somewhat tilted towards the right of the plane. So if you decrease the gain, so that you will get on the imaginary axis. And you can see here from body plot again, like at minus 100 degree, what is the gain? It is, the gain is nothing but minus 5.58 dB, which is nothing but which is telling that to make the system unstable, then we have to add a additional 5.58 dB gain. That is what the gain margin says, which is nothing but if you convert into multiplicative gain, it is nothing but 1.9. So everything gives the same value, and if you see here, the body plot also gives the frequency is 1.41, and here also if you can see here, the frequency is 1.41, so approximately 1.4. So basically like all these methodologies should be giving the same values of the critical frequency and the same value of the ultimate gain. So by doing different methods, you should not get different values, so that keep in mind that one. So now again, like what is this omega c equal to 1.41, what does that imply? It implies that when gain is not equal to 1.9, the system is going to oscillate at this frequency of 1.41. So that's what we saw before also. So when we increase the gain by 1.9, when we multiply the gain by 1.9, then that is when the system will go into oscillations. And at what frequency will it oscillate? It will oscillate at the frequency the angular frequency of 1.41. So why if you ask the question why, because that is when we can see the Ball-Costen's rule, and then you say this comes around the sine wave goes in phase at that frequency, it comes around the loop in phase, and then it has the gain of equal to 1. So it keeps oscillating at the frequency of this particular omega c, at which the phase is in the sine wave is in phase around the loop. So that's what we saw. So this critical frequency is nothing but will tell the frequency at which the system will oscillate when the gain is increased to 1.9. So that's what, when the gain is equal to the critical gain, that is when the system will oscillate at the critical frequency. That's something you can think of. So this is in omega c is nothing but angular frequency. So we will convert it into normal frequency. So we know that 2 pi f is nothing but omega c. So f is nothing but omega c by 2 pi, or the frequency is nothing but 1 by time period, right? 1 by time period equal to 1 omega c by 2 pi, which means time equal to 2 pi by omega c. So if you can calculate the time comes around, I think around like 4.48. You can substitute the values of 1.4 and then see all these things. It comes around 4.48, which we can see here. Basically we can pick this waveform, we can pick this period. So a sine wave starts here, it completes one oscillation here, and then it completes one oscillation here. So basically within 10 seconds, basically it completes 2 times, and it has some more gap. So basically 4.48 should be working, right? So that's what we can see, approximately 4.48. If this is 4.48, this is 4.48, it's value. You can zoom it and see, basically it will become equal to 1.48. That's what you can see here. So so basically that everything, see, even if you plot and see, you will be able to find the value of the critical frequency. Even by plotting, you can find the time period of one sine wave here, and then with this time period you can find omega critical frequency by just back substituting. You know the time period, and then you can find omega c, and that should be around 1.41. So just remember this, all these methods should give the same value. That's what we are seeing. And then Ziegler-Nichols method, there's a table. So from Wikipedia I have taken this table, that lot of tables. So basically what you do, once you find the ultimate gain, that is Ku, and once you find this is T, nothing but the period of oscillations, the tu is nothing but time period, which is nothing but t u is nothing but what you we have derived in the previous slide, what you have seen 2 pi by omega c, basically 2 pi by omega c. So, we have calculated the tu value. So, once you know the value of ku and tu, ku is nothing but the gain at which the system will go unstable. So, once you know the value of ku and tu, you can just substitute these values and then just find the value of kp, ti, td and etc. That is what you can directly substitute, and you can ti is nothing. So, basically you can write ki is nothing but kp by ti, and kd is nothing but kp into td. So, that is what you can just substitute and see here. It will be like you will be getting the getting this k and kd value. So, basically lookup table, you can just have it in a paper and then just find these values of ku and tu and then just substitute this into that, and then you can see that. So, there are a lot of rules, like this is not the only rule that we have, a lot of rules that we have. So, basically that is what. So, and one more thing that we can say here is like there are some kind of like some other tables, no? So, it says like some overshoot, no overshoot. So, this you can just substitute once you find the ku and tu, you can just play around this with and then see whether this whether this gives no overshoot. So, what is overshoot basically? So, when I want to give a step change in my I want to change the control variable from say 50 degrees Celsius to 60 degrees Celsius. I want to give a step change, and then the control variable actually goes around and then comes like this. So, to what temperature it will reach more than the steady state temperature, that is what is called the overshoot. So, one way to visualize this overshoot, why it is important is, suppose you have a tank, okay, and then you want to change the level from 50% to 80% of tank level. Now, you are interested to ask like if it has a overshoot, whether the tank will like whether the water will flow out of the tank or not. So, basically if you have a tank something like I will just use this. So, if you have a tank it is having like 50%. So, you want to give a step change from 50% to say 80%, just we will take that. So, you want to see whether the level will go outside of the tank level or not. So, if it goes out, what happens? If it crosses under 100%, what happens? The water will flow out of the tank, right, which is not desirable. So, overshoot is kind of like you can think like overshoot, why it is important in such sense. And so, this when you do not want to overshoot, basically you can use this particular formula, you can check this and simulate and see what happens. So, all that you have to calculate is ku and tu, and you can use different methods for ku and tu. You can use Raoult array, you can use root locus, you can use Bode plot. So, everything works, everything should give the same value, and then you find these values and then you substitute, you use this any of these formulas whatever you desire, or not. This is not the only set you have a lot of rules available. You can do the literature survey and then you can find it out and then you can substitute and then see what happens. And this classic PID is another thing that is like mostly people why it is like interesting is because what it says is like I will have a decay ratio of 1/4. So, if you have something like this and then settling like this, what it basically says is if you see this amplitude and this amplitude, say you call it as a A and you call it as a B, then what it says is B will be nothing but it will be like 1/4 of the A, that is what it says. So, that is what 1/4 every time it decreases by 1/4 value, 1/4 times it decreases basically. So, A will be 4 times bigger than the B, that is what it says. So, this is another way of tuning. So, all these things are for different all these things are like some formulas for some objective. So, there are a lot of ways you can get this gains of PID controller. So, you can just play around with all these things and then you can try it for yourself. For illustration, we have just taken a simple PI controller. Basically, we have used this particular formula and then this is what the output we got, and then this is the response we got. So, this is just for illustration. You can just try with yourself and with something, and then you can verify how each things behave. That is what. So all this is for getting an intuition of all these things do. So, when we did a lecture on what the effect the PID gains have on system. So, now we use different tuning methodologies and then say okay, this is better for this thing, and for this application this seems better, and this application this seems better, etc. And everything has its own advantages and disadvantages. So, only like there are a lot of rules available. So, that you can just see. So, now next method we are going to see is like Cohen-Coon method. So why this method is like interesting is this is the next widely used method. Cohen-Coon is next widely used method that you are going to have. So here what we are going to do is we are going to get a FOBDT model. So FOBDT model is nothing but the first order and plus dead time process. So any like any system you can represent it something like 1 by k by 1 plus tau was into e power minus ds. So this is something that you can represent any system. So let us say like you have been given a plant, and let us say you are having say boiler. We will take the boiler as example again. So let us say I am giving you a system. I am giving you a system. I ask you to tune the PID controller for it. So what is that you are going to do? We may not actually from first principle start deriving all the things, right, the heat equations and then energy balance equations, energy conservation, etc., and finally derive. That is one way of doing this. The another thing is like I have a system, I have it now, like can I do something quickly to tune the PID controller? And because like for my first method of deriving from first principles is using approximations, and then even that is not a very great methodology because that also uses some approximation. So why don't I just use the system I have and then I play with it? So that's what I can do. So what I'm going to do is basically I wanted to maintain the set point to be like around 80 degrees Celsius. So what I'm going to do is I'm going to give a step change around like close to 80 degrees Celsius. Okay, so what I'm basically doing, I'm using the g of s. I am giving a step change. I am giving a step change in the inflow, like the manipulated variable. So I am giving a step change in the manipulated variable of g of s, and then see how the output changes. For example, if it is a boiler or something, what I am going to do, I am going to just put more fuel to it, so that I am giving a step change in the fuel, and then I am going to see how it is going to, how the temperature is going to vary. So this is going to vary something like this. So and now with this can I get a model? So my objective is to do this experiment to get a model. So basically to get some coefficients and then use this coefficient or model to get some PID values, so some Kp, Ki, Kd values. So that's what it's happening here. So this is the Cohen-Coon method. So we will try to see for the same system, for a system like this, what is the like, let us say like this is what I have got the response. So basically what I have done, I have given a step change in the manipulated variable at time equal to 0, and this is what I have got as a response. So basically this is how my output is going to vary. So what are the values I am going to get from this, and how I am going to use these values for getting the controller's parameters. That is what I want to see here. So now here, if you can see here, basically I will just redraw things here so that it will become easy for explaining. So I have given a step change in the manipulated variable. So this is what I am giving a step change in the manipulated variable, and now what happens? This is u, okay, and what happens? My output is going to change like this, okay. So it's going to go to like this. So it's something we can see. And first thing what I am going to see is, see this actually looks like it starts after some time, right? But actually maybe actually it started here, but it was not growing so fast. So this is one thing I see, and then I can visualize this as something like it's a first order response. I can visualize this as a first order response. See, I will say this is a first order response which is starting after certain time. So this I will call as a dead time. So I can consider this as a first order response with a dead time. So that's what I can think like this. So actually this is not a first order with the dead time. Basically this has started increasing here itself, but it is slow enough, and then after a while it starts behaving like a first order system. But I will, for everything is an approximation. Here also I am just approximating things, and then what I am going to do is I am going to just take this as a dead time and then a first order system. So it's basically like the first order system responds something like this, and I am just shifting it. I am delaying it by time, by a dead time. That's what I am visualizing this like this, and then I am going to find what is the first order dead time process model. So basically what it means, I am having first order model which is actually having a delay of d seconds, the ds. So this is what dead time is about. This is the dead time basically. D is a dead time. So now what is the way I can look at? What I basically do is I will draw a slope basically maximum in this line. What is the maximum slope I can draw? So basically I can draw something like this. So in this time I can just draw something like this slope, and that point at which it intersects the x-axis, that distance, that time, what time it intersects the x-axis, that time I call as dead time. So I can do this as a d, and then what I can do from first, since it's a first order, I assume this is a first order response. What I can do, I can tell like at 63.2%, right, or 0.623 of the total value. So if here it is 2, so at some value around 2 into 0.632, which is like 1.2 something. So here somewhere around, this is what is the time that is there, that is the time constant, right. So that time constant I measure after the dead time. So after dead time, whatever is the measurement, that is what I am going to do. After dead time, what is the time constant, that is what I am going to see here. What is the time that reaches after dead time, I estimate for dead time, what is the time that that it takes to go to 0.632 of the total steady state value. So steady state value is 2 here, so this is nothing but 1.2 something. So this we have seen from the first order response thing. So the time, what is the tau is, the time constant is nothing but the time taken to reach 63.2% of the steady state value. That's what we observed from the first order systems thing. So that's what we are applying here, and then we can find tau like this. And what is the gain? Gain is nothing but for step change in the input. So this change is u is 1, I increase by 1. What is the final change I get here? So basically let us call it as delta y, and let us call it delta u. So if I give a delta u change, how much change that delta y has happened in steady state conditions. So steady state conditions is like this here. So if I give a step change, if it has become 2, so basically it means for u delta u equal to 1, for a unit step change I am getting delta y equal to 2. So gain is nothing but 2. So I get a gain equal to 2, and dead time equal to around say 0.5, and this tau looks like around 1, right. So my so this is like 0.5 to 1.5. so this is like tau is 1. So basically this particular system is nothing but approximately 2 by 1 plus s e power minus 0.5 s. So this is how we get the various values of dead time, time constant, and gain. So gain is the delta y by delta u input, like how much fuel I added, that is the input, that I changed the fuel, that is delta u, that is the input. So delta u is the change in the input I have given, and delta y is at steady state what is the output change that has happened. So that is the gain. Delta y by delta u is the gain, and then d is nothing but if you draw a slope where it intersects, that's what the dead time, after what time it started responding, that's what basically it means. And then tau is nothing but after this dead time, to reach 63.2% of the final y value, that's what is the time it takes, that's what the tau is nothing but. So this is how we can find the FOPDT of the system, and that's what basically is given here. Maybe you can go through this, and then once we have the value of k, tau, and td is nothing but dead time, we can use this table to find the values of k peak, va, and PID, k peak, ka, and kd. So that's what we can do it here, and so this is nothing but so ka is nothing but kp by tau y. That's what we have already seen how to convert from time constant to the gains of integral and derivative when we did it for Ziegler-Nichols. So yeah, that is what. So you can try this Cohen-Coon, and then you can see how it works, how it performs. So it's just some play with values, and take some system transfer function, plot the graph, and then take the FOPDT, and then see what happens, etc. And then if you are interested, there are lot more concepts in PID controller, even in industries. Like when we use if you go to the actual plant, like there are lot more practical constraints in implementing a PID controller, and something is called bumpless transfer. What is bumpless transfer, and what is the integral windup? So we have integration. If you have a PI controller, it has an integration in it, and what happens when this integrate, this goes to a very high value, and like you can just read through all these things. These are all like some interesting things you can just read through, which we are not covering, but just some it's all available in the internet you can just go through this what is a bump-less transfer and what is interval interrupt, etc. So basically you can play with all these things, and you can try to implement something in MATLAB using this bump-less transfer and interval interrupt and see what happens. So which may be some exercise for something interesting to do. So yeah, thank you.